Dear students, so today we will discuss solar radiation energy on your horizontal flat plate collectors. So what we are considering here, our surface is horizontally, collecting surface is horizontally placed, and the solar radiations are coming directly normal to that. We are not considering any tilting in the collector plate. So before directly coming to the energy discussion, let us start from the energy curve, that is relates the time of the day and the insolation incidence on the surface. It is named as LZ. It is time of the day, So during the noon, we'll mark few points: sunrise and sunset. If we plot the energy curve, then we find, we have studied this already, we discussed it. This is the probable curve, and the energy, this is the LZ is the insolation incident normal to the horizontal plate, and this is the time of the day, and this region tells us the energy available for full day from sunrise to sunset in the radiation. So just mark the points. LZ is known as insolation incident on the surface. Normal to the horizontal flat plate, horizontal flat plate, and the unit can be kilowatt per meter square, insolation unit, that is we know already, and the power in it is H0, we assumed it H0. So this is the total energy available from sunrise to sunset in the solar radiation, that is H0. We can say daily for one day, so we can say daily energy present or available for a horizontal surface this is energy, so unit can be kilowatt hour per meter square per day. Okay, now to find the total energy of a day, what we have to do, we have to find the area of this region, and to find the area we should discretize this, make a small portion, this length times this thickness will give us the area of this region, and for this region we do like that, and if we will add up all of them, then we can get the full area of this region. So to find the full area, just we have to sum of all the areas part by part, or we can say that is the integration of full day of LZ with respect to the dW, where this is the hour angle. So here we can write W is the hour angle. To make the things clear. So this is the term that defines the total energy available for a day in a solar radiations coming to the flat plate collector. Let us redraw the energy curve that we can say somewhat like that. This is sunrise, this is our angle omega, okay. This is sunrise and this is sunset and this is noon, okay. It is considered as omega is equal to 0. Omega is considered as omega SR. Omega is considered at this point omega SS. So the total energy of this region will be H naught, okay. So from here we can again write H naught as from omega SR to omega S set sunset of LZ into D our angle, change in our angle. So if we are considering it 0, then this angle is, anyway this is the fundamental assumption, this is considered as 0 and the rise time is considered as positive and this is negative in terms of angle. So this angle is considered as positive angle and this angle is considered as negative angle. After a while we will draw the angle curve, then we will explain the our angle from there. So for time being, consider this is positive, this is negative, and from there the second assumption that is made is this angular length and this angular length is considered as equal. So the second thing we can say omega SR is equal to omega SS, we can say, okay. In that case the magnitude is same, however this is the minus of this, so we can say the final minus initial, it should be from final minus initial. I think there is something wrong, so it should be final initial, it should be from sunset to sunrise, the minimum to maximum, okay. So from here what we can say, this is minus sunrise plus sunrise LZ dW. Further it can be written as, since this is symmetry, almost it is considered as symmetrical, this is the symmetrical axis, so this portion is almost completely symmetrical, so this limit can be transformed into 0 to omega RS. We can place this 2 here, LZ. Now if we consider the earth somewhat like that, and this is our collector and radiations, this is normal to that, it is L, it is Z, zenith axis, and the radiations coming normal to that is LZ. So LZ are the radiations coming to the collector surface. However, at the atmospheric top surface, it is different than that. So the relation between LZ and L can be written as sine delta sine phi plus cos delta cos phi and cos our angle, okay, where L is the extraterrestrial insolation. Extraterrestrial insolation level. Okay, this is declination angle, we came to know yesterday. This is latitude angle, we already know this, and this is our angle, we will calculate later. However, just at this moment I will show you how these angles are formed when solar radiations are coming to the Earth's surface. So let us try to understand. So the name of these two we have studied: latitude, declination, and hour angle, and this is the extraterrestrial insolation level. So at the Earth's surface, if we can receive this radiation that relates to these parameters. So for example, to understand these angles formation, let us revise once again. This is, consider a spherical shape of the Earth. Okay, this is the equatorial plane, you can say. Equatorial plane, and you can form you can say meridian axis, it can be said here. And this is polar axis. Okay, so east to west, polar north to south. Anyway, now the main point is radiations are coming incident radiation is coming like that. Okay, its projection on the XY, or you can say equatorial plane, is this projection on equatorial plane. This angle is known as delta, that is available here. Hopefully it is okay. And this is our incident radiations. Okay, and this angle is our angle, that is measured from meridian axis. So you can say W is this angle, and this is our declination angle. Now let us try to find the phi, and to find the phi, assume any location. Let me choose another color. This is point P at the Earth's surface. This is the plane parallel to the equatorial plane. You can say north and south, east and west. Okay, don't be confused from this and this. So the line that is normal to this plane, how we can say this line, that is zenith axis. When we will make like that, because it will be radial vector, that's why it will match to that. This line with the meridian axis, this axis, the angle formed will be phi. Hopefully the things are clear now. The phi is, suppose the observer is here, means the collector is here, and the collector is the parallel to the equatorial plane. Okay, so the line that is normal to the collector surface, if we extrapolate that, then the angle between meridian axis to that line joining to the center is called latitude angle. So that is here. So for time being, we will discuss only these few angles. Later, if it is required, then we will discuss else. Okay, and okay, the radiations are coming here like that. Okay, the radiation with the projection of this, the angle between this radiation and this axis is our delta, that is already discussed, and this with respect to z, this with respect to south pole is gamma s. Okay, and this incident with this zenith is called theta z, sun azimuth angle. It becomes very complex. Anyway, the main angles are clear to us, that is required to find LZ, to find the H0. So this plane is, you can say horizontal plane, and this is the local centric coordinate, you can say. Okay, local centric coordinate. If different angles, delta, hour angle, phi, and many more came to know, that are required to find LZ, that is required to find the H0. Now we have all of them. So let us start finding H0 once again. So from here it is 2, 0 to sunrise hour angle. LZ can be written from here, that is L cos, this term first I am writing, cos delta, cos phi latitude, cos hour, okay, plus sine declination, sine latitude. Hopefully it is not creating any confusion. Just I am placing this LZ in terms of these and hour angle. We are integrating with respect to hour angle. What will be the unit of this? Unit of this will be kilowatt radian per meter square. This is for 1 day, so per day, for a day. But our interest is not to find the power radian per meter square per day. We have to find the power. This is the term extraterrestrial insolation, that is the term we will discuss later, but let us continue. our interest is to find the kilowatt hour, that is the energy unit. So for that purpose, we will talk after few minutes. Just continue this. 2L, integrate this, cos delta, this is the independent of omega s, omega, this is also independent of omega. This is the term that will be sine omega, and it will vary from omega SR. Same way for this is independent of this term. So sine delta and sine phi omega, it will be 0 to omega SR. Hopefully it is okay. Okay, so let us continue. 2L, put the value here, cos delta cos phi sine omega SR, or and 0, sine 0 will be 0, so only this term will be left and remaining term will be 0, plus sine delta sine phi, and omega will be now omega SR. Okay, and this is still in kilowatt radian per meter square per day. However, our interest is to transform into energy unit in kilowatt hour. So let us continue. For full day, 2 pi radian is covered in 24 hours. So we can say pi radians are equal to 12 hours. Then omega radian will be covered in 12 by pi hours. Sorry, it will be for 1, it will be for omega. Hours. Okay, so this is the constant term. This is conversion factor, you can say. Factor. Okay, so if we wish to find the energy in terms of kilowatt hour, then we can say H naught will be equal to the 2 times L times 12 by pi, that is conversion factor from radian to kilowatt hour, and multiplication of the remaining terms, that will be cos delta declination angle, cos latitude, sine hour angle of during rise time, plus rise time hour angle, sine declination and sine phi. Here the unit will be now from kilowatt radian. Due to this factor, it will be kilowatt hour per meter square per day. So this is our final requirement. So let us continue with this. To find the H naught, declination angle is known, latitude angle is known, this and this, these two terms are known. What is unknown terms is rise time and the extraterrestrial insolation level. Okay, so these two terms are still unknown. So to find the total energy in the solar radiations, let us try to find these two terms. So let us mark them, L and and L is the radiation energy that is available at the extraterrestrial region, and the term is already defined for that. L is equal to LSC, that is mean solar constant. It is termed as LSC 1 plus 0.033 cos 360 by 365 n. This is the term already defined for L with the help of solar constant, where n is the number of day of the year, n is equal to 1 for January 1 and 365 for December 31. So in this way we can find the value of n, and if we know the value of n, at what day we are trying to find the energy in the solar radiation, and LSC solar constant, that is known term. So L solar constant is already defined 1.3, I think that is, if I am right, 1.37 kilowatt per meter square solar constant. I think you should verify this term, but as I remember this is 1.37. So once you know solar constant, that is already defined, and you know the number of day at for what you are talking about, you are trying to find the energy level, then you can find the value of L, that is known to us now. From here, still unknown is this term. Okay, so now we will try to find the sunrise and sunset hour angle. So I think for today we can stop at this point. To find the sunrise and sunset hour angle, we will continue tomorrow. Thank you very much.